In section 9.3, we look at how gases behave in chemical reactions and also in mixtures of other gases. So many times chemical reactions will result in either the formation of a gaseous product or the consumption of a gaseous reactant. Now that we know about the ideal gas law, we can conveniently calculate the number of moles of a gaseous reactant or product and perform stoichiometry calculations similar to what we would do for an aqueous solution or a solid. So a good example of this is the following question. It says, how many grams of sodium chlorate are required to produce 125 liters of oxygen at 1 atmosphere and 20 degrees Celsius according to the following reaction? And the first thing that we should think about is that the temperature here, we really want to remember to be working in Kelvin. So that's going to be 293.15 Kelvin. Okay, so if we recall the ideal gas law, PV equals nRT, you can see that we can calculate the number of moles of oxygen quite simply. So our pressure, P, is 1 atm. Our volume is 125 liters. R is the ideal gas constant, 0.0821 liters atmosphere per mole per Kelvin. And then finally our temperature was 293.15 Kelvin. And so hopefully you'll be able to see that atmospheres will cancel out, kelvins will cancel out, liters will cancel out, and the only units we have remaining are moles. So the number of moles of oxygen produced, that we're trying to produce in this reaction, I should say, ends up being 5.1937 mole. Now, we know that for every mole of oxygen, we need 1 mole of sodium chlorate. So this works out pretty easy to calculate the grams of sodium chlorate. All we have to do is multiply our moles of O2 by our mole ratio relating the number of moles of sodium chlorate to the number of moles of O2, and then multiply by the molar mass of sodium chlorate to convert the moles of sodium chloride into grams. And if we check our units, you can see that everything works out. And when I do that to three significant figures, it works out that I need 553 grams of sodium chlorate. We can also combine the gas law with other relationships that we know. For example, we know that the ideal gas law is PV equals nRT, but we also know that the number of moles of a substance can be calculated by taking the mass and dividing by the molar mass. So what I can do is I can take this expression here and use it to replace N. This gives me the following. PV equals the mass times by the ideal gas constant multiplied by the temperature divided by the molar mass. Now what I'm going to do is I'm going to move volume over to the right hand side. And you can see that it'll give me this. And what immediately leaps out is this term here, mass over volume. Because if you recall from our previous work, mass over volume is the same as the density. So what I'm going to do is I'm going to move everything to the left other than the terms for mass and volume. And that gives me this. The pressure times by the molar mass divided by the ideal gas constant multiplied by the temperature is equal to the density of a gas. This can also be reorganized to get an expression for the molar mass of a gas. dRT on P gives me the molar mass. And these two relationships are really helpful. The first one tells us a few interesting things. It tells us that as temperature goes up, the density of a gas goes down. That is, that density and temperature are inversely proportional. It also tells us that as the molar mass goes up, the density goes up. So that's really saying that density is directly proportional to molar mass. So if the temperature was fixed and the pressure was fixed, what gas would we predict to be the least dense? Well, we would predict the gas that has the lowest molar mass. And that, of course, is hydrogen with a molar mass of 2.02 grams per mole. So our equation for the density of a gas tells us that if everything else is constant, then density is directly proportional to molecular weight. And so the gas with the smallest molecular weight is hydrogen, and consequently that gas has the lowest density. So it's for this reason that hydrogen was chosen to fill balloons way back in the early days of ballooning. Now, of course, there's a slight problem because hydrogen is really, really combustible, and I've got a little video that'll show you this. So this is, of course, the famous docking of the Hindenburg that went wrong. And just as it touches the tower, the whole thing bursts into flames, and a whole bunch of people died. And there we go. You can see just how quick it burnt. Another little video here illustrating the combustibility of hydrogen. This is more controlled circumstances. So hydrogen burns with a characteristic sort of popping noise, and so it makes a pretty loud bang when it does burn. The equation for density for the density of a gas also tells us that density is inversely proportional to temperature. That is, as the temperature of a gas increases, its density goes down. So a safer form of ballooning is hot air ballooning, where we control the density of the gas simply by controlling its temperature. Okay, so here's an example problem using our density relationship. So this reads, a gas has a density of 0.65 grams per litre at 25 degrees Celsius and a pressure of 757 millimeters of mercury. What is its molar mass? So what we know is that the density of a gas is given by Pm on RT. So we can reorganize that to get an expression for the molar mass. So dRT on P will equal the molar mass. So I always like to look at the units of R to remind myself of what I need for the units for everything else. So R has units of, or has a value of 0.0821 with units liters, atmosphere, per mole, per degree Kelvin. So that tells me that my temperature has to be in Kelvin, which will be 298.15, and that my pressure must be in millimeters of, must be in atmosphere. So that means that I'm going to have to divide by 760 because there are 760 millimeters of mercury in 1 atmosphere. So let's put all of this together. My density is 6.5, oh, so not 6.5, 0.65 grams per litre. R is 0.0821 litres atmosphere per mole per Kelvin. And then my temperature is 298.15 Kelvin. So this is going to eliminate litres, and it's also going to eliminate Kelvin. Okay, and now we have to divide this by the pressure in ATM, which is going to be 757 on 760 ATM. So now we can cancel out ATM, and the only units that we have left are grams per mole, and to three significant figures this works out to be 16 grams per mole. And there we go. By measuring the density of a gas, its pressure and temperature, we're able to confirm its molar mass, which is kind of fun. So we learned a little bit about how gases behave in chemical reactions, or how to work with gases in chemical reactions, and we got sidetracked by calculating things about the density and molar masses of gases. Another interesting problem to consider is how do gases behave in mixtures. And to begin with, we're going to think about how mixtures of non-reactive gases behave. So kind of like how the atmosphere around us behaves. And it was Dalton, the same guy who studied the atomic theory, who figured out how mixtures of non-reactive gases behave. And this is known as Dalton's law of partial pressures. And Dalton's law of partial pressures states the total pressure of a mixture of gases is equal to the sum of the partial pressures of the gases. So what does that all mean? Well, the partial pressure of a gas is the pressure a gas in a mixture has if you were to imagine it was the only gas present. So imagine that we have 3 equal sized containers. One of them has 10 particles of gas A in it. One of them has 5 particles of gas B in it. And the third one has 5 particles of B and 10 particles of A. And if we look at the pressure of the first one, we might measure that to be 10. We look at the pressure of the second one, would measure that to be 5. But when we look at the pressure of the mixture, well, we find that it is a pressure of 15, which is just the sum of the pressures of the gases when they were in the container by themselves. That is, the pressure of the mixture is equal to the sum of the partial pressures of the gases. So having them together in the mixture doesn't make any difference. The gas behaves as though it was the only gas present. That is, the total pressure is just equal to the sum of the partial pressures of however many gases we have in our mixture. So here's a little example. The total pressure exerted by a mixture of O2, N2 and water vapor is 754 millimeters of mercury, so just a little less than 1 atmosphere. The partial pressures of N2 and O2 are 154 millimeters of mercury and 320 millimeters of mercury respectively. What is the partial pressure of H2O? Well, this is what we know. The total pressure is equal to the pressure of H2O plus the pressure of N2 plus the pressure of O2. And we know that the total pressure is 754 millimeters of mercury. We don't know what the pressure of H2O is. we do know that the pressure of the nitrogen is 154 millimeters of mercury and that the O2 has a pressure of 320 millimeters of mercury. So it's pretty easy to solve for X. 754 minus 154 minus 320 equals X, and that equals 280 millimeters of mercury. So that's a classic Dalton's law of partial pressures problem. When we're talking about mixtures, we can use the mole fraction to express the proportion of a substance in a mixture. So the mole fraction, which we indicate with the symbol chi, is just equal to the number of moles of X over the total number of moles. And it's always worth noting that the mole fraction of some component X will always be less than 1, but when you add together the mole fractions of all of the components in a mixture, it will always add up to 1. So if it is 0.6x, then if we have a mixture of X and Y, and it's 0.6x, then it must be 0.4y, because they have to add up to 1 in total. So we won't work through the math, but it can be easily shown that the partial pressure of any gas in a mixture is the product of its mole fraction and the total pressure. So that's really easy, right? The pressure of any component is equal to the mole fraction multiplied by the total pressure. So if the total pressure is 1 atmosphere, and half of the moles of gas present are of what we're interested in, then the pressure of what we're interested in would be half an atmosphere. Very easy. So that concludes the video for section 9.3, stoichiometry of gaseous substances, mixtures, and reactions. I hope you found the video helpful.